Alright, so now we're going to start 1.4. 1.4 is inductive reasoning. As you see, there is a P up top because this would be where we would start class. This is our bell work. So take out your sheet of paper that you're going to do your today's participation on. Go ahead and put bell work on the first line, your name, date, and block on the top right corner, and answer these questions where I'm asking you to find the midpoint and distance between the points. So that's the distance formula and the midpoint formula. And then after you answer these on the bell work portion, go ahead underneath that and write participation for 1.4, and then we'll start the lesson. If you need to pause it to get the points, that's fine. There's no graph here. The other video had graphs, but we can just start right off on the points this time, so you don't have to look at the graphs. You have P and Q and R and S. So you're going to find the midpoint of PQ. You're going to find the distance between P and Q. Then you're going to do it for R and S for both of them again. So basically, inductive reasoning is looking at information you're giving. Use knowledge you already have. Sometimes it's just common sense. Sometimes it's I'm looking at it. Here's the next piece to the puzzle. And then you were going to try and figure out if you can see a pattern in all of that information. It's can be really hard and difficult at sometimes. Sometimes it's very easy. Let's look at something. So if I gave you this sequence 1, 2, 3, 4, 5, 6, and I asked you what comes next, we could pretty confidently say that 7 is going to be the next thing we're going to do. 1, 2, 3, 4, 5, 6, 7, then 8, 9, 10. It's the previous number plus 1 over and over again. So that's a pretty easy pattern. Now if I gave you this one, 1, 3, 5, 7, what do we have there? Looks like the odds. Or you take a term, add 2 to get the next one, then with your most current term. So 1 plus 2 is 3, 3 plus 2 is 5, 5 plus 2 is 7. We can use inductive reasoning to say that 9 should be next. That's pretty easy, right? Just plus 2 plus 2 plus 2. This is the most important part for inductive reasoning. There must be a minimum of 3 pieces of data to establish a pattern. If you're only given 1 or 2 pieces of data, you cannot establish a pattern, and I'll show you why in just a second. So what number comes next in this sequence? 1, 2, and remember we only have 2 pieces of data here. We could say 3. That actually, if you ask most people, they would probably just say 1, 2, well 3 is next. But in this sequence, it's actually 4, and what we're doing is, if the next number is 4, we start to see a pattern. So what would the next number, the 4th term, so this is term 1, this is term 2, we just said the 3rd term I gave you for the 3rd piece of data is 4. So now that we know that, what can we assume, or what can we, using our inductive reasoning, what can we come up with for the 4th number? Well, the 4th number would be 8. And now we have the pattern. We have 1, 2, 4, 8. And if we look at that, it looks like if I do 1 times 2, I get 2. If I do that term times 2, I get 4. If I do that term times 2, I get 8. So it looks like what the real thing, or the pattern here, is multiply the largest term by 4. Or 2, sorry. So, as we saw above, a pattern cannot be established with less than 3 pieces of information. Keep that in mind. That's going to be on your quizzes. That's going to be on your test. There's going to be questions where you only have 2 pieces of information, and I say use inductive reasoning to find the 4th term. You're not going to be able to without the 3rd term there. Alright. So when we do this, the way I recommend, especially when we're starting, once you get used to it, you can kind of start seeing patterns and pick it up and, you know, pull it out of thin air. But I would really recommend start with a table. It lines up everything. It gives you the term number and what its value is, and you can start seeing the relationship between the term number and its value. So the nth term is a generic piece of data in the data of a pattern. What that basically means is, if I ask you for the nth term, or n equals 5, I'm asking you for the 5th term. We'll apply the 5th, n equals 5 into an expression that we can come up with from the data using inductive reasoning to find the value of that term. So let's look at one. So here I have, this is my n term, so this is n equals 1, and the value when I plug it into the function is 1. Here I have n equals 2, and I get 4. Now I have n, that's my 3rd term, n equals 3, and that gives me a value of 9. My n equals 4 is 16. I don't have my value for n equals 5. We're going to figure that out using inductive reasoning. But when n equals 6, the value of the expression is 36. If you see a pattern already, you're on a strong start for inductive reasoning. If you don't worry about it. It takes seeing quite a few of these to get it down really well. Excuse me. So 1 to 1, that can be anything. That can be 1 plus 0. That can be 1 times 1. It can be 1 squared. It can be 1 to the third, 1 to the fifth. 2 times 1 minus 1. There's a million things that 1 can be. So that one piece of data does not tell us anything. Now we have our n equals 2 and we get 4. So now we're starting to develop something. So before I said it could be 1 times 1 to get this. Well, 2 times 1 does not give me that value, so we can discard that. We're going to start shedding all of these other assumptions that we had, or ways we could have went from n equals 1 to a value of 1, and we're going to try and lock into a pattern here that produces 1 when n equals 1 and 4 when n equals 2. So think of that, it could be 2 times 2 is 4, but 1 times 2 is not 1, so that's starting to be a problem. Now I did say 1 squared is equal to 1, and now I'm looking at this 2 squared is equal to 4. That could be our expression that's generating the values for each term. So let's look at it. 3 squared is 9, 4 squared is 16. So let's assume that we are just squaring the nth term to get a value that is equal to the nth term squared. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, and 6 squared is 36. That fits the pattern really well. It looks like we're going to take n, raise it to the second power, and we'll get our value for the table. So why I recommend using a table, it works out so well. So now, yeah, if I ask you on the quiz just what is the value of n equals 3, we would go up here. We would see that 9 is the value, so we can say n equals 3 is equal to, its value is 9. What is the value of the sequence at n equals 6? So I'm going to go into the n, go across that row, go to n equals 6, and see that its value is 36. So now we already discussed the pattern here, and that's just n squared is equal to the value for it. This is just a visual representation of what we just talked about. If you want to see it written out, this is what I said. Just, pause the video, check it out. Now I'm going to ask you on your participation, what is the value of n equals 8? Put that down in your participation. It's not going to be on a slide, so it's just if you're watching the video, I know you saw it if you give me the value of n equals 8. Alright, so let's look at a different one. So now this time I'm given 1 to 1. So my nth, when n is 1, my value is 1. Here's the problem. I don't know what 2's value is. So right now we already broke the chain. These three, n equals 1, n equals 2, and n equals 3, already doesn't have enough information to establish a pattern. But fortunately, I do have n equals 3, n equals 4, n equals 5. There's 3 in a row. I'm going to find my pattern from here. And then I'm going to go back, and using my inductive reasoning, I'll say I should be able to find whatever expression generates this value. When I plug n equals 2 in, I'll be able to fill in this blank, and then this whole value row should be valid, and we've used inductive reasoning appropriately. You do not always have to start at n equals 1. You can start at n equals any value as long as you have 3 consecutive terms, and then work backwards, work forwards. So what do we do? If we look at the values, the value row, we can see that the numbers, when we start with 1, then we don't know, and we have 5, 7, 9. That's adding 2 each time from n equals 3 on, right? So we can assume that it's just, when we fill in this table, we can use inductive reasoning now to see that we go from 1 to 3 to 5 to 7 to 9. But here's the hard part about inductive reasoning. What expression fits and fills in this table? I can't say n plus 2, because n plus 2 would give me, for 1 plus 2 is equal to 3. So we're not just adding 2 each time, we're not adding 1 each time. We actually need to come up with a sequence that can generate each of these values. So let's start at 3. Is there any way to get from 3 to 5? Well, I can add 2. So let's see if that works for 4. If I start at 4 and I add 2, I don't get 7 though. So let's go back to 3 and see what else can we do to generate 5 when n equals 3. So if I do 2 times 3, I get 6. If I subtract 1, I will get 5. Let's do n equals 4. So what I did there was I said 2 times the nth term minus 1 will generate our expression, is what it's looking like. So let's put that down in writing. So I'm saying that 2 times n minus 1 should give us the value we're looking for. So let's look back at the screen. So if I did this, I would have 1, or 2 times 1 minus 1 would give me 1. 2 times 2 minus 1 would give me 3, which should be this if these other patterns, if these hold for to be true. 3 times 2 is 6, minus 1 is 5. 4 times 2 is 8, minus 1 is 7. 5 times 2 is 10, minus 1 is 9. 6 times 2 minus 1 is 11. So it looks like we're on the right path here. So let's look at it as if when n equals 2, our value is unknown. So if I apply this conjecture with this term, I should be able to tell you the value for that term. So 2 times 2 minus 1 is 4 minus 1, which is 3. So for n equals 2, the value is 3. And that works because on the other page we have 1, the value is being 1, unknown, but we're saying it's 3 now. 5, 7, 9, 11, so plus 2. So now we're going 1 plus 2 is 3, plus 2 is 5, plus 2 is 7, plus 2 is 9. So that's what we're doing. That's it right there. We've just found a conjecture. We've tested it with the data available, and this is exactly what I would want to see on the quiz or the test. You would show me you think this holds true for all the data that you've been given. Then you go back and you use the unknown, the nth term that is unknown, and you substitute the value of that nth term to see what this expression generates. And it generated 3, and then we ended up with our values being 1, 3, 5, 7, 9, and 11, which is plus 2, plus 2, plus 2, plus 2, plus 2. That's really all inductive reasoning is. It's increasing, just like we said before. We can see that the numbers increase. They increase by 2. This is working. So 2n minus 1 is generating the values we want for each nth term. This is a conjecture. This doesn't mean it's true. It doesn't mean it's wrong. This is the very basis for proving that something is true. This is the very basis for proving something is false. Alright, so now what we just came up with, this expression is called a conjecture. We know from n equals 1 through n equals 6 it holds up. And let's test n equals 6 real quick. 2 times 6 is 12, minus 1 is 11. That checks out. So this conjecture holds for all of the data that we have available. In a higher level math course, if you go to college, you want to major in math, once you get through all the calculus sequence and stuff, you'll actually get to proving that this holds for all real numbers, but we're not going to do that in this class right now. That's beyond the scope. But this conjecture we made, this 2n minus 1, holds true for the values we're given, so we're going to go ahead in this class and say that is all we need to do for inductive reasoning. So think about that. I know we're doing this a little bit differently because I was sick, but in class, just so we get used to it, this is where we'll kind of have a discussion here and say, you know, in your groups, discuss an expression that returns the correct values. We've already generated that expression. If you can find another one, that would be awesome, and I might actually award an extra credit on the quiz if you come up with another expression that generates those. And if you can't, show me that you tried and we'll see what we can do. Alright, so now let's start moving to the abstract. We've used inductive reasoning to find patterns in numbers. Let's see if we can do it in pictures. This works. Remember, you don't trust your eyes, but if you can show that something continually works, is true, we call that inductive reasoning, and we're going to try it with pictures. That's a little bit weird, but we're going to use those pictures, we're going to use the information given, and find numbers that line up with it so we can start doing it. So, what conjecture can be made about the number of dots in the nth term of this geometric pattern? So, for my first term, I have 2 dots. For my second term, I have 6 dots. For my third term, I have 12 dots. For my fourth term, I have 20 dots. Notice that the number of columns is 1 more than the term number. and the number of rows is the same as the term number. What does that mean looking at this picture? So the number of columns is one more than the term number. So columns are vertical. These are columns. And they are one more. So if I have term 1, I have 2 columns. Term 2, I have 3 columns. Term 3, I have 1, 2, 3, 4 vertical columns. And on 4, I have 5. 1, 2, 3, 4, 5. So that's our first thing. And then the number of rows is the same as the term number. So rows are the horizontal slides. So if I'm on term 1 going left to right, that's 1. Term 2 going left to right, I have 1, 2. Term 3 going left to right, 1, 2, 3, and so on. So we can start looking at relationships and see if we can force a pattern out of them that we can then test on excuse me, other terms. So if term 1, 2, and 3, if we can find a pattern there, then term 4, we can test that pattern or that expression or that conjecture we generate. And if term 4 if the conjecture or the expression satisfies terms 4 number of dots, we can say at this point in this course that we have used inductive reasoning to come up with a conjecture that satisfies this problem. So now we're going to look at an algebraic expression to generalize the pattern for the nth term. Since the number of rows in the pattern is equivalent to the term number, use n to represent the number of rows. So we're going to use, this is going to be our n term, and this is going to be our value. So for n equals 1, my rows are n. They're equivalent. N is equal to n. So on 1, I have 1 row. On my second, n equals 2. On term 2, I have 2 rows. Term 3, I have 3 rows. Now this is the complicated part of this. Columns, I have 1 more than my n value. So n plus 1 is 2. So if I go to 1, I have 2 columns. That's the vertical ones, 1, 2. And my rows are horizontal, that's 1. Same again here. If I have 2 rows, then I have 3 columns. If I have 3 rows, then I have 4 columns. And again, 4 rows is 5 columns. So this table does work. When n equals 1, I have 1 row, which is true, and I have 2 columns. Perfect. So we're on the right step here. But this is a lot more information than we had in our last chart. So what can we do with that? Let's take a general term chart, or let's take our general term chart. General terms include the variable n, and compare the chart to a second chart with our picture. So now I'm starting to see more and more information, and I'm getting 1 to 2, 2 to 3, 3 to 4. So it's still, again, my rows are matching, and my columns are just my rows plus 1. But we still haven't really found a pattern yet. Nothing obvious. They're always increasing by 1, but that's obvious by this right here. N is this, and n plus 1 is that. And then when n is 2, that's plus 1. So this is all working out. We've set the chart up right, but we still haven't found our pattern yet. So consider the number of dots and the relationship they share to the number of rows and columns. So let's go back here. So rows and columns. I have 1 row, 2 columns. How many dots do I have? I have 2 dots. That might be something. 2 rows, 3 columns. How many dots do I have? I have 6. I'm starting to see a pattern here. If I have 3 rows and 4 columns, if I follow this same pattern, I'm going to end up with 12 dots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Or more quickly, 1, 2, 3, 5, 1, 2, 3, 4. 4 times 3 is 12. I think we're starting to find the pattern. This should be 20 dots. So now that we're seeing it, now we're starting to get a pattern here. And our pattern is the number of rows times the number of columns is the number of dots. This is just area. This is exactly what area is. Length times width. So if I do length times width, I have 2 times 3, and that's 6. So when my term is 2, I multiply it by the number of columns, and I get my number of dots. If you have any questions on this, please do not hesitate to ask me in class. In person, we can go over it in class, so you can ask all your questions as it unfolds. Tutoring is on Thursdays after school. Alright, so now let's look at another conjecture. This is a little bit harder, but let's see. The conjecture is the nth term of the sequence will contain n times n plus 1 or n squared plus n dots. Now if you want to know why these are equivalent, if I distribute n into here, I will get n times n, which is n squared, plus n times 1, which is n. So I'll have n squared plus n. These are equivalent expressions, and either one of these would be the correct conjecture to write for this test. So let's look at n squared plus n on this chart. So n is 1. N squared plus n would be 1 squared plus 1, which gives me 2 dots. My second term, n equals 2, gives me 2 squared, which is 4, plus 2 dots. N equals 3 is 3 squared plus 3, which is 9 plus 3 is 12. So that's how this works. This conjecture, written either way, is perfect for your homework, for your test, and for your quiz. Now, let's talk about using counterexamples to prove a conjecture is false. And this is where our symbols are really going to start to come into play a lot too. We talked about this in class. You should have all this written down. This whole line is able to be condensed into just this. This is what we're going to be working on in this class. This is how we're going to be writing these in this class. Of course, not right away. But if I were to say n words, if n is a rational number, then n squared is greater than or equal to n. In symbols, I read this as if n, that's our variable, is an element of, means it's contained inside of the rationals or is part of the rational numbers, then every time we take n and square it, it'll be greater than or equal to n. Recall that a rational number is anything that can be expressed as a over b, and it terminates or repeats. So 1 over 4 is rational because it terminates to 0.25. 1 over 3, which is 0.3 repeating forever, is rational because it follows a pattern. Something like pi, which never repeats, never terminates, is irrational. So this doesn't work. Pi is not in the scope of this question. But the number 1 is, because 1 can be expressed as 1 over 1, which terminates to 1. 2 over 1 is 2. 6 over 4, all of those, if the fraction part repeats or terminates, you can use them in this conjecture. So let's test the conjecture. So what it says is for all n, there exists for every n that is part of the rationals, anytime I take n and square it, it'll always be greater than or equal to n. So if n is 1 and I square it, I get 1. 1 is greater than or equal to 1, so that holds because they're equal. And that equal, then, when you're reading these problems, you really have to pay attention to the conditions, and that's why in symbols it makes it much easier to follow, because 1 is equal to 1, we're good there. Now if n is equal to 2, 2 squared is 4. 4 is definitely greater than or equal to 2, so that passes. 3 squared is 9, that passes. So far this conjecture looks great. But in a section of this topic where it says use a counterexample, of course there's going to be a catch. So we still haven't found our counterexample, but we do need to really look at this conjecture in full. So far we've only tested natural numbers. A natural number is any number that you can count on your fingers, starting at 1. And then, of course you would join other hands and stuff, but starting at 1, 2, 3, 4, 5, all the way to infinity, those are natural numbers. We've only tested natural numbers. The natural numbers are a subset of the rational numbers, meaning there are more rational numbers than natural numbers. So we have to kind of broaden our scope and not just test these easy ones. We have to make sure we fully understand what a rational number is, and that we've tested as many examples as possible with or without finding a counterexample. So let's look at 3 over 1. That reduces to 3, and 3 squared is 9. Still works for this conjecture. 8 over 4 is 2, and 2 squared is 4. So 2 is still less than or equal to 4, so we're good to go. But now we're going to run into a problem. 1/2 squared is 1/4. Let's look at that on the other screen. So if I take 1/2 and I square it, boy, that's a bad circle. So if I start with 1/2, and then I square it, I'm going to end up with 1/4, which is only this section. So now I've ended up with less. So here's our counterexample. Because we found something that when we started with 1/2 and squared it, we actually ended up with a smaller number. So there's our first counterexample. Now, this would be a perfectly adequate answer to show me a counterexample, because that does show that the conjecture is not true. If you want to really shoot for the extra credit, we can talk about that. And I'll show you what I would like you to do for extra credit. And we're not going to be so precise as you would in a higher level course. So now, we see that if the number is less than 1, it still doesn't work. I mean, the conjecture falls. But what if we use the negative number? So let's try -2. If I square -2, I get 4. So it works for that negative number. Let's try one more. That's also true. And then, of course, for all of you out there that said, wait a minute, you only have 2 data points here, not 3 like you just said we had to have, we're going to do one more. -7 squared is 49. 49 is greater than or equal to -7. So those all hold there. So now we kind of see a pattern for negatives working. What about -1? That's kind of a weird one. -1 squared is 1, so that still works. What about 0? 0 squared is 0, that still works. So it seems like just fractions, proper fractions, seem to not be working. If I did 1/100, I would get 1/10,000. That's definitely not true. 1/10,000 is not greater than or equal to 1/100. So it looks like all numbers, except for the numbers greater than 0 and less than 1, work for this. So that's our counterexample. You can stop right here on the quiz or test, but a great extra credit question would be, find a reasonable range for possible counterexamples. And a reasonable range here, you can show me that 1/100 squared is 1/10,000, and 99/100 squared, whatever it is, will be, you'll end up with a smaller number still. And that's exactly what I would want to see. You can say it looks like from 0 to 1, this fails. And I can say 0 to 1. Let's do between. Between 0 and 1, this fails. That means 0 is not included and 1's not included. But every real number in between, or every rational number in between, is included. Provide a counterexample for each conjecture. If no counterexample can be found, then write this conjecture is true. So this is your participation. This goes on your participation sheet. We had the other question where you found n equals 8, I believe, for the other problem that wasn't written down. Make sure this goes after that n equals 8 problem for me. Go ahead and pause the video because I'm going to move on to the next slide. And then tell me, make sure you understand these numbers. You can always look them up or message me about them. They should be in your notes. I know my Tuesday class may not have had a chance to get them. Alright, so here's inductive reasoning in a nutshell. Words leads to a conjecture, which is something we do have to prove by observing patterns. So we started off looking at numbers, finding a pattern, then testing that pattern, and saying, yeah, it looks like it holds true for all of the data that I asked you to find. And then we also looked at a problem where I gave you a wider range, and you kind of had to narrow it down and figure out exactly where it doesn't work. And that's what inductive reasoning is. Uses specific examples to make a generalization. Those generalizations then are conjectures that can be proven true or false, and does not show that a conjecture is true. So a conjecture could be disproven by a counterexample. Yeah, conjectures are not always true. We can look at a lot of numbers, we can look at patterns and start somewhere, but as we add data, see that our narrow view of 4 data points wasn't sufficient when we had 100 data points to find that pattern. I'll try and think of an example, and I'll maybe post it on Edsby, where the first 3 points of a thing work great, but when we have 20 points, we realize it does not work anymore. So, and here's our diagram. We just have a pattern that 0 squared plus 0 plus 11 is 11. 1 squared plus 1 plus 11 is equal to 13. As the pattern continues, the sum is a prime number. It's pretty interesting, actually. So every time we do a number, we take a number, square it, add that number to that, and then add 11. We seem to always end up with a prime. So, conjecture. If n is a whole number, then n squared plus n plus 11, which is exactly way up here. This is our n term. So we have n squared plus n plus 11 is equal to a prime number. It's going to, naturally at this point, we'll ask you to find a counterexample. And we can say that if we have n equals 11, we end up with 11 squared plus 11 is 143, and that is divisible by 11. So the sum is not always prime. That's perfect counterexample. That's all I would ask for. I couldn't ask for anything more, to be fair. All right, your homework is on Edsby. There's a video now showing you how to find the homework. If you have any trouble with it, message me. In a little bit of time between the first video and the second video, I've had 3 people ask me, and I think it's been a lot easier to just kind of talk everyone through it, because there's certain parts that are hanging up people in different ways.